Okay, so you want to run artificial intelligence at scale. The plan in your head is not complicated. You buy the GPUs, you rent or build a building, you connect the internet, the models run, the money follows. It is a clean, modern digital operation. No raw materials, no heavy machinery, no smokestacks. Technology companies are supposed to be light, scalable, frictionless. Here is what the press releases never mention. Every single one of those GPUs is essentially a small electric furnace wearing a circuit board as a disguise. The moment you turn it on, it starts converting electricity into two things simultaneously: computation and heat. An enormous, relentless, structurally unavoidable amount of heat. A single NVIDIA H100 GPU draws somewhere between 300 and 700 watts of electrical power, depending on workload. One chip. Not a rack, not a row. One chip the size of a hardback book. Run 1,000 of them in a facility, and you have a heating load that would comfortably warm every apartment in a mid-sized residential building through a Scandinavian winter. Except you are not trying to warm anything. The heat is waste. Expensive, persistent, equipment-destroying waste. And getting rid of it is one of the largest and least discussed costs in the entire artificial intelligence industry. A data center can buy all the GPUs it wants. Without cooling, they become very expensive space heaters. Let's talk about why that is, what it actually costs to fix it, and why the economics of keeping silicon cold are stranger and more consequential than almost anyone outside the industry ever thinks to ask about. Modern AI accelerators are not like the processors that run your laptop. A laptop chip draws 15 to 45 watts under heavy load. A smartphone chip draws 3 to 8 watts. These devices were designed with the assumption that a human being is sitting nearby, and that heat output needed to stay within the range a small fan and some aluminum fins can manage. Nobody wants a laptop that requires a radiator. AI training chips operate under entirely different constraints. The limiting factor is computational throughput, and throughput scales with power. More operations, more heat. The engineers at the chip companies made a deliberate choice to keep increasing power envelopes because customers buying GPUs at $30,000 to $40,000 each are not sensitive to electricity bills. They are sensitive to training time. A cluster that finishes a training run in 3 weeks instead of 5 weeks justifies almost any power cost. So the chips got hotter, and hotter, and hotter. By 2025, a single modern AI server chassis designed around 4 to 8 high-end GPUs produces a thermal output of 10 to 30 kilowatts per rack unit. In older data center designs, the standard assumption was 5 to 10 kilowatts per rack, total, for the entire cabinet. The industry did not gently evolve toward higher densities. It ran headlong into a thermal wall at speeds that left much of the built infrastructure obsolete within a few years of being constructed. Buildings considered state-of-the-art in 2018 needed significant retrofitting by 2023 to host the chips the market was demanding. That retrofitting is not cheap, and it is entirely unavoidable. The original cooling technology for data centers is the same one that cools your office building. Push cold air over hot things. Computer room air conditioning units, which the industry calls CRACs, with no apparent sense of irony, blow chilled air through raised floors into the hot aisles where servers exhaust their heat. The hot exhaust gets captured, chilled, and recirculated. Simple in concept. The problem is that air carries roughly 4 times less heat per unit of mass than water does. To remove 30 kilowatts of heat using air, you need to move an enormous volume at high velocity across every surface of every server. Get the airflow wrong, and hotspots develop. Hotspots cause servers to throttle their performance. In a sufficiently severe hotspot, servers shut themselves down entirely. This is called a thermal shutdown, and it has the same effect on a data center's revenue as a power outage, except it is entirely self-inflicted and considerably more embarrassing. The industry measures cooling efficiency using power usage effectiveness, or PUE. A perfect PUE of 1.0 would mean every watt drawn from the grid goes directly into computation. A good air-cooled facility achieves a PUE of around 1.4 to 1.6, meaning that for every 100 watts of computing load, the facility draws 140 to 160 watts from the grid in total. That additional 40 to 60 watts goes entirely to cooling and overhead. It never touches a GPU. It never trains a model. It exists solely to prevent the GPUs from turning into expensive slag. At current U.S. commercial electricity prices of roughly 7 cents to 12 cents per kilowatt hour for large industrial consumers, a 10-megawatt AI data center running at a PUE of 1.5 spends between $3.7 million and $6.3 million per year purely on electricity required to cool the facility. Not to run the GPUs, to cool them. The cooling energy budget alone, at industrial scale, exceeds the total annual revenue of most small businesses. That is the cost of not solving the problem. Around 2022 and 2023, the industry collectively admitted what the physics had been saying for years. Air cooling at high GPU densities is increasingly untenable. The solution is to stop using air as the primary heat transfer medium and start using water. Direct liquid cooling, or DLC, brings cooled water directly to the server chassis through cold plates attached to the surface of the GPU die. Water flows past the chip, absorbs the heat, and carries it away to a heat exchanger at the edge of the room. Because water carries 4 times more heat per unit mass than air, you can remove the same thermal load with far lower flow rates, far quieter systems, and far greater precision. A well-implemented DLC system can push PUE toward 1.1 or even 1.05 in optimized installations, while reducing the cooling-related portion of power consumption by 30 to 50% compared to air cooling. The capital cost, however, is substantially higher up front. Installing DLC infrastructure adds between $1 million and $3 million per megawatt of capacity over baseline construction costs. You are paying a large premium at construction time to obtain lower operating costs over the building's lifetime. In markets with expensive electricity, the payback period can be as short as 3 to 5 years. In markets with cheap hydroelectric power, it can stretch to a decade or beyond. There is also immersion cooling, which is exactly what it sounds like and sounds considerably more alarming than it actually is. Entire server boards, including the GPUs, are submerged in a bath of dielectric fluid. The fluid absorbs heat directly from chip surfaces and circulates through a heat exchanger. Immersion achieves PUE values approaching 1.03. The systems are mechanically simpler than DLC. There is just a tank of fluid, a pump, and a heat exchanger. The catch is that immersion requires purpose-built server hardware incompatible with standard air-cooled components, which matters enormously when hyperscalers order servers by the tens of thousands. Immersion also makes routine maintenance considerably more awkward. Pulling a GPU for replacement when it is submerged in warm dielectric fluid is, as one data center engineer described it, like doing surgery in a swimming pool. The fluid is not toxic, but it is slippery, expensive, and very good at finding surfaces it has no business touching. Here is the number that tends to produce silence. A large, air-cooled data center using evaporative cooling towers can consume between 1 and 3 liters of water per kilowatt-hour of IT load. A 100-megawatt data center, a size that the largest hyperscalers now build routinely, can consume between 1.5 billion and 5 billion liters of water per year. A single large data center can consume as much water annually as a small city of 20,000 to 50,000 people. Read that again. Not a city's worth of electricity, a city's worth of water. This is not an abstract environmental concern. In water-stressed regions, which include most of the American Southwest, large parts of Europe, and much of Asia, municipal water utilities are beginning to impose restrictions and surcharges on industrial consumers above certain thresholds. Arizona, which for several years aggressively recruited data center investment through tax incentives, has begun imposing water use agreements as a precondition for large facility approvals. In some cases, data center operators must demonstrate their water consumption can be sourced entirely from recycled or non-potable supplies. Building the supplementary water infrastructure to comply can add tens of millions of dollars to a project. DLC and immersion cooling eliminate the need for evaporative cooling towers entirely. In a jurisdiction where water is becoming expensive or politically contested, the ability to operate without significant water consumption is genuinely valuable, independent of the PUE and electricity cost arguments. This is one of the least discussed economic arguments for liquid cooling, and in certain markets it may turn out to be the most decisive one. You have built the facility. The GPUs are running. The heat is being managed. Now consider what happens over the next several years. Because cooling infrastructure is not a set-and-forget installation. It is a complex mechanical system with pumps, valves, heat exchangers, sensors, actuators, and control electronics, all operating continuously, all subject to wear, and all capable of failing at inconvenient moments. The standard service contract for a large data center cooling system, covering preventive maintenance, emergency response, and parts replacement, runs between 3 and 8% of the original equipment cost per year. For a facility where cooling infrastructure represented a $30 million capital investment, the annual service contract sits between $900,000 and $2.4 million. Every year, for the lifetime of the building. These contracts are not optional in any practical sense. The cooling vendors who designed the system hold proprietary knowledge about its integration, control software, and failure modes. An operator who declines the service contract discovers quickly that the technical documentation for complex liquid cooling systems is written in a language that exists somewhere between mechanical engineering, software development, and optimistic fiction. The vendors know this. The pricing reflects it. You are not just buying maintenance. You are buying the right to call someone who knows what went wrong at 3 a.m. when the primary cooling loop pressure drops unexpectedly and the monitoring system begins sending alerts faster than anyone can read them. Beyond service contracts, there are the consumables. Cooling water in a DLC system requires continuous chemical treatment to prevent biological growth, corrosion, and scale buildup inside cold plates. The biocide and corrosion inhibitor program can cost $50,000 to $200,000 per year in chemicals alone. Immersion cooling fluids must be replaced on a cycle of 3 to 7 years. A full fluid replacement for a large immersion system can run $500,000 to $1.5 million for the fluid alone. None of these costs appear on a GPU vendor's datasheet. They live quietly in the operational budget, growing steadily as the facility ages. Here is where the story gets genuinely expensive. A GPU running a training workload operates close to its maximum safe junction temperature by design. The thermal margin between running optimally and beginning to throttle is often measured in single-digit degrees Celsius. When a cooling system fails, the timeline to damage is not hours, it is minutes. A modern GPU operating at full training load with cooling interrupted can reach its thermal shutdown threshold in under 5 minutes. A rack of 8 GPUs with failed cooling can experience irreversible component damage within 10 to 15 minutes if workloads do not gracefully terminate before shutdown occurs. In 2022, a cooling system failure at a European co-location facility caused a thermal incident that took down servers belonging to multiple cloud customers and reportedly destroyed components valued at several million euros. The operator faced customer claims, regulatory inquiries about SLA compliance, and a public disclosure requirement under data protection law because affected servers held customer data at the time. All of this because a pump failed. This is why cooling redundancy architecture is not an engineering luxury. The standard design uses an N+1 or 2N redundancy model. For a 10-megawatt facility, this means roughly doubling the cooling capital investment. Building one cooling system costs $20 million. Building two in the same facility costs $35 to $40 million because the systems share some infrastructure. The additional $15 to $20 million buys you the ability to continue operating while one cooling train undergoes emergency repair. For an AI cloud provider whose customers are paying $2 to $8 per GPU hour and running training workloads that may take weeks to complete, the economic cost of a single unexpected thermal shutdown can dwarf the entire annual maintenance budget of the cooling system that failed to prevent it. Let's build a realistic picture for a mid-scale AI data center, a purpose-built facility hosting 5 megawatts of high-density AI compute, roughly 500 to 800 high-end GPU servers. Land and building shell, $15 million to $25 million. Power infrastructure, including the substation, backup generators, and UPS systems, another $8 million to $15 million. Cooling infrastructure with appropriate redundancy for a 5 megawatt DLC facility, $25 million to $40 million. This is the number that surprises almost everyone who has not looked at it closely. The cooling system alone represents 30 to 40% of the total facility construction cost. Not a supporting line item, not an afterthought, the single largest or second largest capital expenditure in the building. The GPU hardware for 5 megawatts of AI compute, call it $150 million to $250 million. The building that houses and cools those chips costs roughly 1/4 to 1/3 of what the chips themselves cost, and that ratio is climbing as chip power densities increase. Annual operating costs, electricity for compute and cooling combined, at a PUE of 1.15 with DLC, roughly $3 million to $5 million per year. Service contracts, water treatment chemicals, and periodic fluid changes, another $1.5 million to $3 million per year. Staffing with trained engineers capable of managing liquid cooling, another $500,000 to $1.5 million per year. Total operating overhead before debt service? Somewhere between $5 million and $9.5 million per year. For a 5 megawatt cluster that might generate $20 million to $50 million per year in GPU rental revenue, this is a meaningful and non-trivial cost structure. The cooling is not a footnote to the economics, it is a chapter of its own. Here's the thing that the entire cooling economics argument ultimately points toward. You are not really in the GPU business. You are not in the AI business. At the fundamental level of what your facility does every day, you are in the heat management business. Everything else, the GPUs, the networking, the software stack, the customer relationships, depends on your ability to continuously extract heat from a building faster than the hardware inside it generates heat. The moment that balance shifts, even briefly, everything above it in the value chain is at risk. The companies that understand this most clearly are investing in next-generation cooling technology before they need it. They are signing long-term water supply agreements in regions where water access is uncertain. They are building relationships with cooling equipment manufacturers that give them early access to systems capable of handling the 50 kilowatt and 100 kilowatt rack densities the next generation of AI accelerators will demand. They are treating cooling infrastructure not as a supporting system for the compute, but as the foundational system upon which all compute capability depends. The companies that understand it least are currently deploying high-density AI clusters in buildings designed for 8 kilowatt racks, adding supplemental spot coolers as the thermal situation gradually deteriorates, and hoping that nobody notices the GPU throttling that shows up as unexpected variance in training job completion times. They have bought the most expensive sports car on the market and installed it in a garage with a 30-mile-per-hour speed limit. The car works fine. The infrastructure is the constraint. The GPU is the headline. The cooling system is the foundation. And foundations, as anyone who has ever paid for one knows, always cost more than you budgeted for, take longer to get right than you planned, and cause considerably more problems when they fail than anything built on top of them. The press release will say you built an AI data center. The invoice from the cooling contractor will remind you what you actually built. A very sophisticated, very expensive machine for turning electricity into warmth that also happens to train language models on the side.